So we'll start, everybody. So first of all, thank you, Ettore, for giving this talk to us. So this is in the context of our seminars in the program of mechanical engineering here in UFRJ. I'm going to briefly introduce Ettore Saetta. So he's a postdoc research fellow in the Department of Industrial Engineering of the University of Naples, Federico II. And his research activities concern machine learning algorithms for aerodynamic applications. And he earned his master's degrees in aerospace engineering in 2020 and PhD in 2024. So he's a fresh PhD in the University of Naples. So the title of his thesis was Machine Learning in Aerodynamic Clustering of Autoencoders for CFD Applications. And since 2021, he's collaborating with Stanford University on the development of autoencoders. And 2023, he was awarded with the Stanford Foundation Scholarship to support his activities as visiting researcher at Stanford University between October 2023 and 2024. So it's a pleasure to have you here. And so he's mainly going to talk about the autoencoders in aerodynamics, and autoencoders are becoming a very hot topic in machine learning. So thank you once more, and you can start.
Thank you, Ronnie, for the introduction, and also thank you for inviting me to give this talk. So now I'm going to share my screen. Okay, can you see my presentation in full screen?
Yes, you can see.
Okay, so today I'm going to talk about multi-fidelity autoencoders for aerodynamic analysis. And this is a research activity developed by Professor Tognaccini from the University of Naples, Professor Iaccarino from Stanford University, and me. I would like to give you a brief overview of our research activity about autoencoders. So we employ autoencoders for real-time flow predictions, in particular of aerodynamic interest. And we worked on some of the open challenges on autoencoder research. First of all, the interpretability of the learning procedure of autoencoder. Then we worked on developing an algorithm for reducing the amount of data required to train an autoencoder, or a deep learning in general. And we worked on the uncertainty quantification of autoencoder prediction. So this is a fundamental topic for the safe deployment of such algorithms in real-world applications. All of this work were published on journals. And I would start with a quick overview on what an autoencoder is. So let's start with some of the motivations. So these that you can see here is an unsteady run simulation around an airfoil with a periodic pitching motion, experiencing the aerodynamic dynamic stall. And this is typically done with what is called the full order model provided by a CFD simulation. And specifically these solutions were obtained using the SU2 solver, which on our workstation took 367 hours of CPU time. So these are expensive simulation. And it is also heavy to storage. For example, one of the simulation took 40 gigabytes to be stored. Imagine, for example, an LES simulations, which can also take terabytes to be stored. So we can see two of the limitations of the adoption of such methods, which is we get some high dimensional data, so we need larger storage, and also the file transfer will be very slow. Then they are also computationally expensive, so it is unfeasible with such full order model to get a real-time prediction of the flow field. So we have some solutions to try to solve these limitations. For example, there are methods for data compression to reduce the dimensionality of the data, and there are reduced order models to make predictions with less computational cost. And in this framework, autoencoder are a powerful tool. In particular, they are unsupervised deep learning algorithms, which are mainly adopted for dimensionality reduction and feature extraction. For instance, let's see here the flow field around an airfoil, which can be considered as the input to our autoencoder. It is provided in input to what is called an encoder, which is the first part of the architecture of an autoencoder, which compress this high dimensional data in a very low dimensional latent space or latent vector here in red. Then there is the second part of the architecture of an autoencoder, which is the decoder, which takes in input this very low dimensional latent vector and reconstruct the original dimensionality of the data, making a prediction. So in this case, you can see here that the output of the autoencoder is a reconstruction of the input itself. And that's why this is the reason why the autoencoder is considered as an unsupervised deep learning algorithm. So autoencoders can be seen, making a comparison with classical methods, it can be seen as a nonlinear extension of the proper orthogonal decomposition, which is a linear method. For instance, if you consider an autoencoder like this, so with only one hidden layer, a fully connected autoencoder with only one hidden layer, let's consider linear activation functions and no bias. If you try to write the equation of this very simple autoencoder for the encoder and for the decoder, you will find actually the equation of the POD. But adding many hidden layers to an autoencoder provide, and using nonlinear activation function, provide methods for a nonlinear manifold parameterization. So we get a nonlinear transformation which allows to achieve an extreme data compression even on complicated phenomena. So I will briefly show you also how do we employ autoencoder. So from the training of an autoencoder to the deployment of the generative model. So we consider 4 steps. You can see that 3 of them, the first 3, are made offline. So they are only performed once before getting the trained model. And then there is the last step, which is the only one performed online, which is actually the trained model to make predictions. One thing to notice here is that, yes, we train an autoencoder, but at the end, to make predictions, we only consider the decoder part of our architecture. So now I will show you briefly each of the steps to be more clear. So first of all, we need to construct a database. So we need a database to train our machine learning algorithm. The database can be constructed by, for instance, run simulation, LES, or DNS, or even experiments. And we need some physical inputs. Let's say that we want to construct a database in which the design parameters of our database are 2, for example, angle of attack and airfoil thickness, and we select the input parameters to construct our database. So we perform, let's say, run simulations for each couple of these database parameters provided by these dots. So we will, at the end, we will get a database of CFD simulations in which we change the angle of attack and the airfoil thickness, for instance, and this is what we get. So here on the left, you can see the computational grid of our simulations, and on the right, the solutions. Actually, this is the local Mach number contour, for instance. But we want to provide this database in input to an autoencoder. So as I said before, we consider convolutional autoencoder. So the input to a convolutional autoencoder has to be a matrix. So in order to get a matrix, we need some structured mesh, something like that. So some article in literature, for example, consider an overlay grid, Cartesian grid, on this original CFD grid to make interpolations on this Cartesian grid and construct in this way the input to the autoencoder. We adopt a different solution. So we perform a mapping for an IJ mapping of the CFD simulation. So we define a curvilinear coordinate I running on the airfoil surface and another coordinate J running in normal direction. So in this way, we can construct a matrix which will be the input to our autoencoder. On the right here, you can see the same solution, so the contour of the local Mach number in this new IJ mapping. You can notice here that because there is a thickening of the grid on the airfoil surface, because it is a run simulation, so we want to capture the boundary layer of around the airfoil. In this representation, there is an augmentation of the boundary layer, which is not clearly visible from the solution reported in the physical space coordinates. So at this stage, we have a database of CFD simulations, and we can move to the learning phase, so to the second step of our workflow. So we need to train the autoencoder. So in order to train an autoencoder, but in general, a deep learning algorithm, so a neural network in general, we need to solve an optimization problem to learn the weights of the network, so the trainable parameters of the network, in order to minimize what is called the loss function. In this case, for instance, the loss function is composed by this term in blue, which is actually the error between the input of the autoencoder and the reconstruction, because our autoencoder is trained in an unsupervised manner. And then here there is this term in red, it is a regularization term that maybe will be, I will explain later. While training an autoencoder, the most important parameter to consider, to investigate, is the dimension of the latent vector. So it's the reduced order dimensionality, let's say, of our data. So in this case, for instance, you can see the loss function as function of the number of epoch during the training by changing the dimension of the latent vector. So from 1 to 5, and you can see here that with 3 latent variables, we reach the convergence. So with 3, 4, and 5 latent variables, the loss function does not change anymore, while it's very high when using only 1 latent variable or 2 latent variables. So we perform some sensitivity analysis on the latent vector dimension in order to get the correct value of how many latent variables we need to describe our database. So at this stage, we have a database, and then we have a trained autoencoder to reproduce the database itself. And then we can move to the third step, which is the latent space mapping. This is needed to make prediction in the fourth step. Why do we need the latent space mapping? So the autoencoder at this stage is only able to reproduce the input itself. And the autoencoder is trained without having any additional information about data provided by the user. So we do not have the correspondence between the latent variables of each case and the database design parameters. So we need to create this connection. And in order to do that, there are several ways. This figure shows these mappings, for instance. So here you can see the angle of attack and the airfoil thickness And you can see that each map corresponds to a different latent variables. So let's consider we have 3 latent variables. So we have the latent variables V1, for instance, mapped as function of the angle of attack and the airfoil thickness. So as function of the database design parameters. So we already have the value of each latent variable for the couple of database parameters belonging to our training database, but we do not have the the possible combination of alpha and thickness. So to get all the possible combination of the database parameters, we can perform a polynomial interpolation, we can train a neural network to create this mapping, or we can use radial basis functions, which is our choice. So at this point, we have this mapping. So we know which latent variables correspond to each couple angle of attack and thickness, and we can move to the last step. So we can make predictions now. Let's consider an example. Let's consider that we want to predict the flow field around an airfoil with two new parameters, angle of attack 22 degrees and thickness 12% of the airfoil. And we can use these maps to get the values of the latent variables V1, V2, and V3 corresponding to this new angle of attack and thickness. And we can provide them in input to our trained decoder, which will provide in output the prediction of the flow field around an airfoil with the 12% of thickness and the angle of attack 22 degrees. So after understanding how our autoencoder workflow works, I would like to show you an application in aerodynamics. Let's consider a physical aerodynamical phenomenon. In particular, let's consider the phenomenon of the airfoil dynamic stall. So this is a strongly nonlinear phenomenon, which is separated, which is ruled by flow separation, unsteadiness, and adverse pressure gradient, and so on. And on the right, you can see an unsteady runs simulations of an airfoil with a periodic pitching motion. Here you can see the contour map of the vorticity. And on the top, you can see the lift curve. So the lift coefficient is function of the angle of attack. And we can consider the lift curve as a summary of the physical phenomenon. For example, here you can see that for this case of the dynamic stall phenomenon, there is an hysteresis cycle in the lift curve. Then you can notice that there is a spike at the stall and strong oscillations in deep stall regime. These are given by the formation and separation of a leading edge vortex which leave the airfoil surface. So you can see how complicated is this phenomenon and also how strongly nonlinear it is. So we want to investigate this phenomenon using autoencoders. So first of all, we need to construct a database. So we considered to construct a database composed by NACA 4-digit airfoils, symmetric airfoils, experiencing aerodynamic dynamic stall. So we performed unsteady run simulations using SO2. And these are the parameters of our unsteady simulations, while the database parameters are 2 in this case, which are the angle of attack, which can be considered as the time, because angle of attack and time are related by this relationship where K is the reduced frequency, which is constant for our simulations. And the other database parameters is the airfoil thickness. So here you can see the lift curves corresponding to the airfoil belonging to our database. What we can notice here, other than the complexity of the problem we are investigating, there is an additional complexity in this database, because we can notice that there is a change in the physics of the dynamic stall phenomenon within the database. In particular, you can notice that for thin airfoils, there is a spike at the stall and strong oscillations in deep stall regime, while for thick airfoils, the lift curves are smoother. This is given by the fact that in these conditions, for thick airfoils, the leading edge vortex has no time to separate from the airfoil surface. So we trained an autoencoder with the 3 latent variables and performed the mapping between the database design parameters and the latent variables. And here you can see there's maps. So on the X, on the axis, you can see the time. On the Y-axis, you can see the thickness. And these are the 3 maps of the 3 latent variables. We can extract from these maps the latent variables corresponding to a constant thickness equal to the 13% for all the time steps. And we can provide these latent variables to the decoder, which provides in output a reliable solution around a NACA or 13 airfoil. In particular, here you can see the solution provided by the decoder, the reference solution provided by CFD simulation, and on the right you can see the pressure coefficient on the airfoil surface. You can see that there is a good agreement between the two. So we can try also to see if we are able to extrapolate beyond the latent space, meaning that we are able to extrapolate beyond the database adopted for training. So we can perform the same procedure and extract the latent variables corresponding to a constant thickness of 20%. Once again, we obtained a reliable unsteady runs simulation around the NACA 20 airfoils, which is in agreement with the reference CFD solution. And you can also see that in this case of thick airfoil, there is not anymore this vortex leaving the airfoil surface, meaning that the autoencoder was also able to distinguish between the two physics of the dynamics tool. So concerning the computational cost of doing this, all the flow fields you can see here are generated using only the decoder and are which are in good agreement with the CFD reference simulation. And to perform an unsteady run simulation using SO2, it took almost 360 hours of CPU time. So on our workstation with 16 CPUs, almost 1 day, while performing a prediction with the decoder on the same CPU, it took 8 seconds. But if we perform this prediction on a GPU, it took 0.08 seconds, which is actually a real-time prediction. We can consider it a quasi-real-time prediction. So after showing how do we use autoencoders to make predictions, I will move to the probably most interesting part of this talk, which is the autoencoder with sequential training and adaptive resolution, which is a training method for autoencoder we recently developed. And in order to explain what the AESTAR is, I should make a brief introduction on the sequential feature extraction. So as I said at the beginning, so autoencoders can be seen as a non-linear version of the proper orthogonal decomposition. POD modes extracted, so POD modes are linear and are orthogonal, and they also have a descending information content. So the energy content captured by the first mode is greater than the second, then the third, and so on. And in order to create, let's say, an autoencoder with this same property, hierarchical autoencoders were developed, in which we can obtain latent variables with a descending information content, even if the modes obtained with the autoencoder are non-linear and are also non-orthogonal. So how a hierarchical autoencoder works? So first we train an autoencoder with only one latent variable. Then we train in a second step a different autoencoder in which the encoder extracts only the second latent variable, and the decoder takes in input 2 latent variables, which are one extracted from the encoder, and the other one is the one learned during the first step of our training procedure. Then we can move to the third step, in which we consider 3 latent variables, where we have an encoder which extracts only the third latent variable, and then the first 2 are obtained from the previous steps, while the decoder takes in input all the latent variables. So this means that if we have a p-dimensional final latent space, we need p training steps to train this architecture. This is a tailored architecture in the sense that it's not the architecture of a classical autoencoder, because at the end we will have that the encoder extracts only one latent variable, while the decoder takes in input all the latent variables. So in order to make predictions, we need one decoder, but if we want to obtain a new latent representation of a new case, we will need p encoders, because each of the encoder extracts only one of the latent variables. So in this way, training an autoencoder like this, at the end we will get that at each training step, the energy content decreases. And this is how a sequential feature extraction works with a hierarchical autoencoder. And the AESTAR, this method we developed, is a training procedure for autoencoders without a tailored architecture, meaning that it's a method to train an autoencoder with a classical architecture of an autoencoder. It relies on what is called latent space conditioning. And the latent space conditioning is a method which is able to provide additional information during training to the latent space, which can be, for instance, physical information. So, for example, we can provide some information about the database parameters, or some topological information. For example, we can assume that the latent space should have a certain topology. And this is how a latent space conditioning works. So it is employed during training into the loss function. So for example, here you can see a loss function which is composed by the error between the input and output in blue, which is the main term for training an autoencoder. And then there is this red term, which is the latent space conditioning term, which is composed by actually the error between the latent variables, VP, and CP. CP is a generic certain information we want to provide during training to condition the latent space. So in this way, we will minimize the error between input and reconstruction, because this is the objective of the autoencoder. And we also want to minimize the difference between the latent vector and some information. So we want actually, in some way, let the latent space have a certain shape. In the method we developed, the AESTAR, we named this latent space conditioning an unsupervised latent space conditioning, in the sense that the information we are providing to the latent space is not actually provided by us, but it is determined by the autoencoder itself. Now I will show you what I mean with that. So first of all, we need to train an autoencoder with one latent variable. So with p equal to 1. Then in a second step, we train an autoencoder with 2 latent variables, in which the second one is free to be learned, here in red, while the first one is conditioned to be equal to the one learned previously. Then we can perform an additional step in which we train an autoencoder with 3 latent variables, where the third one is free to be learned, and the first 2 are conditioned to be equal to those learned in the previous step. So actually, this is a sequential training, which relies on a latent space conditioning. And this is the loss function we are employing. So the error between input and reconstruction, as usual in blue, and in red, there is this conditioning term, which is actually composed by the error between the latent subspace of the current step and the latent space of the previous step. So let's see now an example of application of this algorithm to aerodynamic data. So let's consider a physical phenomenon, this time a little bit more simple, which is the aerodynamic static stall in this time. And let's construct once again a database composed by NACA 4-digit symmetric airfoils performing runs simulations. And here you can see the lift curves of the airfoils belonging to our training database. Also, in this case, we have only two database parameters, which are the angle of attack and the airfoil thickness. You can notice that this phenomenon is linear for small angle of attack. So we have a linear behavior of the lift curve as function of the angle of attack. And then the phenomenon becomes non-linear when stall occurs. Once we have this database, we train an autoencoder with the DI star method, performing two steps. So in the first step, we train the autoencoder with only one latent variable, and this is the latent variable we obtain. Now, in this case, we have the latent variable as function of the angle of attack and colored by different airfoil thickness. What you can notice here, the first thing is that we have some kind of linear behavior for small angle of attack and non-linear behavior when stall occur. And we will see later this analogy between the latent variables and the physics of the phenomenon. And then we perform a second training step in which the second latent variable is free to be learned, and the first one is conditioned to be equal to those learned in the first step. So equal to this one, actually. And this is the latent space we obtain. So here you can see V1 versus V2. On the left, the latent variables are colored by angle of attack, and on the right by airfoil thickness. You can notice that the autoencoder was able to learn the database parameters by ordering the latent space in angle of attack in this direction and in airfoil thickness in this other direction. So let's see what are the advantages of training the autoencoder in this way. So I reported here the lift curves of the database airfoils just for reference. And let's see that this is the latent space obtained with the DI star method we already saw. Then this is the latent space obtained with a classical autoencoder, so directly trained with two latent variables. And this is the latent space obtained with the hierarchical autoencoder I explained you at the beginning. So what we can notice, first of all of the methods are able to identify the database parameters by ordering the latent space. But the I-star method better captures the physics of the phenomenon. In particular, you can see that we have a linear behavior for small angle of attack and a non-linear behavior when stall occur. Moreover, if you consider the latent variables corresponding to a constant thickness, let's say the blue curve, you can see also that there is some kind of analogy with the trend of the lift curve of our airfoil. And in particular, if we compute the correlations, so more quantitatively, we can find this correlation. In particular, you can see that here for the I-star on this column, we have a 95% of correlation between the first latent variable and the angle of attack, and a 73% correlation between the second latent variable and the lift coefficient of our airfoils. So you can notice that there is a 95% correlation of first latent variable and angle of attack, also for the hierarchical autoencoder and the classical autoencoder with only one latent variable. This is given actually by the fact that training an autoencoder with only one latent variable correspond to perform the first step of the I-star method or also the first step of the hierarchical autoencoder. So actually these three are the same. So So this is the Aerodynamic method applied to a single fidelity database, but maybe it's more interesting to see that this method can also be employed for multi-fidelity databases, the same method. So in case of multi-fidelity databases, we can train an autoencoder with the latent space dimension equal to P with a certain database. Let's consider which is a low fidelity database. Then we can perform a second step in which we train an autoencoder with a multi-fidelity database, so with the low fidelity database and also a high fidelity database, with the latent space dimension capital P greater than the previous one. And by conditioning the first P latent variables equal to those learned in the previous step. In this case, for the multi-fidelity database, the loss function does not change. So so the algorithm, the method is still the same. And let's see an example now on the advantages of training training an autoencoder with a DI star on a multi-fidelity database. So let's consider the database of airfoils, asymmetric airfoils, by changing only the angle of attack and the airfoil thickness. You can see here now that we are considering the angle of attack range only between 0 degrees and 10 degrees. So it means that we are only considering the linear part of the phenomenon. We are not considering all the lift curves we saw before. And later I will show you also why. So let's construct a multi-fidelity database on this. Let's consider as low fidelity data some Euler simulations, which means inviscid flow, and as high fidelity data some Rand simulations, which means viscous flow. So we also have a change in the physics actually. And the main advantage is the computational time of constructing a multi-fidelity database. So the CPU time needed to construct an Euler to perform an Euler simulation is 95% cheaper than performing a Rand simulation. So this means that if we want to construct a multi-fidelity database with 44 Euler simulations, so all the thickness with all the angle of attack, plus 15 high fidelity simulations, Rand simulations, it corresponds from a computational cost to construct a single fidelity database with only 17 Rand simulations. So this is the database we built. So 44 Euler simulations and 15 Rand simulations. And let's see what's the difference between these low fidelity data and high fidelity data. So actually from considering the pressure coefficient, both simulations provide similar results, but the main difference you can find is in the velocity magnitude. In particular, outside of the viscous region, so in the external inviscid region, they provide similar results, but in the Rand simulations, which are viscous simulations, you have also a boundary layer on the airfoil surface and the viscous wake, which is not present in the Euler simulation. And this is the main difference between the two CFD solutions. And so we trained our iStar with this database. In particular, we performed the first step, training an autoencoder with the latent space dimension equal to 2 on the Euler database. And then a second step in which we trained the autoencoder with 3 latent variables and a multi-fidelity database. So Euler plus Rand simulations. And this is the result we obtained. So here you can see that this is a 3-dimensional latent space. So these 2 plots are the projections of our latent space. In particular, you can see that the black dots are the embedded representation of the Euler simulations, and red dots are the embedded representation of the Rand's simulations. You can notice that the first latent subspace, V1, V2, was conditioned conditioned during training. In fact, you can see that there is an agreement between the black and red, so between the Euler and Ran's embedded representations, while the third latent variable is the one free to be learned, and you can notice that it is 0 for Euler solutions, and it is different from 0 for Ran's solutions, meaning that we can also provide some kind of physical interpretation to this third latent variable, which can be seen as the viscous correction to an unviscid flow. In particular, in fact, considering our trained decoder, we can make some multi-fidelity predictions. So, meaning that if we provide an input, a latent vector, with the third latent variable is equal to 0, it provides an inviscid flow field. While if we provide a latent vector with the third latent variable is different from 0, we obtain a viscous flow field. This means that the same decoder is a multi-fidelity model because it can predict viscous and also inviscid flow field. So it can predict low fidelity and high fidelity data. And we can also say that the third latent variable can be seen as the viscous correction to the inviscid flow. In particular, for example, if you perform some analysis with a very simple panel method, let's say X-foil, you will get exactly the same kind of results of difference between viscous and viscid solutions. And in fact, if we compare the results of our I-star method with an interactive boundary layer method, let's say, for example, X-foil, you will get the same kind of results in terms of difference between viscous and inviscid solutions. For example, here you can see the difference between the pressure, the viscous pressure coefficient and inviscid pressure coefficient for the upper and lower airfoil surface. And so in this way, you are in some ways looking at the viscous correction to the inviscid flow, which for an interactive boundary layer method, it's based on physical consideration. And the autoencoder was able to obtain this kind of correction by itself using the third latent variable. So, as I said before, we are considering a database in the range between 0 degrees and 10 degrees of angle of attack, so only the linear part of the phenomenon. What happens if we consider also the nonlinear part of the phenomenon? So we consider simulations of airfoils which angle of attack ranges between 0 and 30 degrees. This is the result we obtained. So these once again are the projections of the latent space, and in black the Euler embedded representations, while in red the Ran's embedded representation. What you can notice here is that for a small angle of attack, where the phenomenon is linear, we have a good agreement between the Ran's and the Euler embedded representation, while for high angle of attack, we have that the Euler and Ran's embedded representation have the same trend, but we do not have anymore this perfect correspondence between them. Actually, this should not surprise, because for high angle of attack, the effect of the viscosity is not confined in small region near the airfoil. This is because Euler simulation are inviscid simulation, so they cannot predict the stall. So this can be seen also as a way to understand the limitation in our training, in our multi-fidelity database, in the sense that if the two solutions, so low fidelity data and correspondent high fidelity data, are too different one from each other, the latent space conditioning is not sufficient to match the low fidelity data. So in conclusion, we have seen how autoencoder can be employed for high data compression rates and are able also to efficiently represent strongly nonlinear phenomenon like the dynamic stall. And I showed you some an overview of this I-star method, which I want to be clear that it's not a new autoencoder architecture, but it's a new training algorithm for classical autoencoders. And we have seen how the I-star method also provides some insights into the physics of the phenomenon by looking at the latent space. And the I-star can also be employed for multi-fidelity database. So with a drastic reduction of the computational cost to construct the database, and also the model, the trained model, the final model, the decoder in this case, is a multi-fidelity model, so which you can make predictions in high fidelity and low fidelity data. This I-star method was submitted to Journal of Computational Physics, and you can already find a preprint if you need more information and want to deepen, let's say, this topic. I would like to leave you with some references. These references are relative to many things that I showed you during this presentation, and this is the end of my talk. Thank you for your attention. If you have any question, I'll be glad to take them.
Okay, thank you very much for your talk, Ettore. It's really a lot of things which I found really interesting. This last thing about multi-fidelity, I think is a very promising approach, because combining different sources of data is something that I think is really useful. And that thing about the steps was really amazing. So I want to call the attention for the fact that this is a really interesting approach in which you can see that people, in order to do good stuff, they need to match physics with machine learning. So it's not a purely machine learning thing in which you just put the inputs and get the outputs. You have a lot of physics behind, and a lot of physics that are guiding the steps in order to improve the machine learning predictions. So I have some questions, but I will first open. Unfortunately, you cannot see the audience, but we have like 30 people here. And so I will open for questions. I'm not sure if you can hear them. So I would like, if there is any question, you to speak really loud, or maybe you can come back, you can come here. So Ettore, please, please tell me if you are hearing the audience or not about their questions.
Okay.
I have a question about
What's your name? So ask the question very loud.
I have a question on the multi-fidelity part. You go from
Can you hear him?
No, I cannot.
So if you could come, sorry about that. But even though the mic is not
when you start increasing the neurons in the latent space, is that a reason why you go from low fidelity to high fidelity? And if you try to go on the other way, like you start increasing from high fidelity to low fidelity, the number of neurons in the latent space.
Okay, I lost your first question because the connection was lost, I guess. I only heard the second one. Can you repeat the first one, please?
Is there a reason why you go from low fidelity data to high fidelity? Why is this order in the increasing of the number of neurons in the latent space?
Okay, yeah, so actually we go from low fidelity data to high fidelity data because let's say that this multi-fidelity database is a way to have many data, let's say, but with less computational efforts. Let's consider in this case, so to perform just few high fidelity data, just a few high fidelity simulations and many low fidelity simulations. So the idea is that let's say our baseline is a low fidelity data, and we want to augment with high fidelity information. So it's like the baseline is low fidelity because it's simple, it's easier to do, and then we want to provide additional information with high fidelity. So the idea is that high fidelity should provide additional information to a baseline, which is the low fidelity. That's why we move from low to high, because it's like adding information, moving from low to high fidelity. I don't know if I answered to your question. Can you hear me? Can you hear me? Can you hear me?
o Mix aí da vida.
Ele tá no link, ele entrou no link.
Não, no link do Mix você abre um outro
Ah,
aplicativo.
do
Porque o Zoom não tá indo.
O problema é que
Ele-
também aqui.
funciona. Na verdade, ele conectou aqui, tem uma conta logada aí, só clicar no Mix e abrir uma reunião. Aí pior que
O programa é no Google Meet?
tem uma conta logada aí.
É no Zoom?
Não tá com aqui, conectou já direto o.
Pelo Wi-Fi?
Não, no aplicador, eu tô na sala.
Sim, mas você conectou pelo Wi-Fi.
Wi-Fi. Pô, vou te falar como é pergunta. Será que não tem como fazer pelo celular, não, Rony? Eu consegui entrar na sala. I join for browser. O que quer dizer, Rony? Esse eu acho que vai funcionar.
Vai funcionar o Zoom, você fala?
Eu acho que é o programa do Zoom dentro do computador que não está respondendo mais. Vamos ver.
Será que é o programa que você trouxe?
Não, o programa está conectado.
É o mesmo programa?
É o aplicativo dali. Ele está entrando, isso aí é o programa. Tá ele aqui conectado. Está entrando.
Pelo menos acabou.
Tá vendo daqui que ele não vai sincronizar com a sonorização da. O que não vai sincronizar? Ele está conectado, mas ele vai te escutar, mas ele não vai sincronizar com o áudio da sala. Você tá falando com ele, ele falou com ele sobre o. Não,
Você entrou
no computador que não tá aqui no dentro. O problema é que quando ele responder, o áudio não vai sair na sala. É verdade. Não é porque não tem.
Você pediu para ele permitir o acesso? Por que ele não dá o acesso?
Não, tá liberado.
que tem.
Tá devagar.
Tá pior que a conexão Wi-Fi?
Não, mas eu acho que não é nem tempo, porque eu tô no Wi-Fi, eu tô usando o Wi-Fi aqui.
Mas o Wi-Fi de repente está melhor do que o
Não vai mudar, não. Notebook tá não. É melhor, posso tentar aqui. Tem uma conta logada aqui já no Google, é a sua? Não, não. Tem uma aqui. Mas é do Anderson. É do Anderson. Pode ter. Isso aqui já era. Se ele der o. Eu tento dar o join ali pelo aplicativo. Sim, isso não funciona, não. Se você for, você tem uma conta. Mas tem uma conta logada aqui. É. Eu só bati essa cara do criador aí. Aí, o meu não tem cabo, aliás, no Wi-Fi.
Esse aqui vai ter mais. Ele vai. Consegue fazer ali. Agora vai. Anyway, let's work. So we have. Isso.
Pode.
Por que a câmera não está me vendo?
É que eu tô no.
Hi, Ettore. Can you share your screen again with your presentation?
Yeah, sure.
Sorry about the technical issue.
Yeah, no problem. Don't worry. Can you see my screen?
So can you speak again just to see if we are hearing?
Yeah. Can you see the screen?
Ah, isso não tá desabilitado ali o.
Okay, can you speak again, Ettore?
Yeah, can you hear me? Can you hear me well?
Now I can hear
Okay.
you.
Okay,
So
perfect.
did you understand the question?
Yeah, I can remember the question. So
Okay,
uh,
go ahead.
yeah. So the question was, why do we move from low fidelity data to high fidelity data and not vice versa? So the idea was that we can see the low fidelity data as let's say a baseline, in the sense that the high fidelity data should be like more adding more resolution to our data. So it's like we are adding additional information to our low fidelity data, and this is the idea we wanted to keep in training our autoencoder, in which in a first part we have some baseline, which is low fidelity, and then we want to add an additional information by adding an additional adding variable, which is the mapping between the low fidelity to high fidelity. In fact, we want actually to move from low fidelity to make predictions in a high fidelity rather than the opposite. That's the reason why. But it's a good question, I think, for the point of view of better understanding the the behavior of such kind of algorithms, in the sense that maybe once can try to do the opposite, and so make a training on high fidelity and then on low fidelity and see what happens. But we didn't try it. I don't know if this answers to your question.
Yeah.
Or okay.
Okay, thank you. Is there any other question? So
So I just would like to thank you for the presentation. It was really interesting, mainly the second part of it. And my question is regarding the training process. It seems that when you start a training of um, an autoencoder, it's an optimization problem. So you have an initial condition that normally is random. So each time you train your autoencoder, you're gonna probably have a different result, not the same, but somewhat a little different. So my question is, you showed that one of your variables distinguish between the viscous solution and non-viscous one. My question is whether if you keep training, you always give you the same result, or you have different values or different ranges of values, but you still have, in terms of qualitatively speaking, the same result. So you always distinguish between these two solutions.
Yeah, so thanks for the question. It's a very interesting point because I have to tell two things on this aspect. So first of all, when we adopt the multi-fidelity method, we first train an autoencoder with the first step. Then when we train the second autoencoder in the second step here, we do not reinitialize the learnable parameters randomly, but we consider as initialization of the learnable parameters of the second step, the parameters learned in the previous step. So it's like restarting the training from the previous step. This is the first point. Then, in general, if you consider that you perform two different trainings in which the initialization of the learnable parameters is random in the two trainings, in order to take into account of this aspect, we made an article about the uncertainty quantification of the autoencoder prediction, and we saw that substantially the latent representation we obtain are qualitatively the same. Are qualitatively the same in the sense that quantitatively the latent space can be rotated or maybe expanded, but qualitatively at the end we will get the same the same shape, let's say the same topology of the latent space with the different trainings. And moreover, specifically in this case of the multi-fidelity database, we performed this kind of uncertainty quantification. And in this case, you can see here that all the dots here, the red scale, let's say, dots, are thus obtained by 50 different trainings when restarting the learnable parameters equal to those learned in the previous step. And you can see that actually they are quite around these the first step latent values. So in general, yes, let's say that quantitatively you won't get the same representation, but the shape of the space would be the same.
Okay. Another question of the same.
So the second question is in terms of architecture. You have a convolutional part, and then I think you have a feed-forward part. So my question is regarding this point. What is the actual importance, for example, to have these two layers that are feed-forward and connected to the convolution? Have you tried to, for example, eliminate those and see what happens?
With eliminated those, you mean eliminated the fully connected part?
Yeah, just pure convolutional, for example.
Yeah, well, actually, this was not the objective of this activity in the sense that if you make a pure convolutional autoencoder, you won't get a bottleneck. So it means that you won't get some latent variables. But in the lowest part of the dimensionality of our network, you would get a matrix, let's say something like that. So you would get some like an image, let's say, but not let's say coordinates. But we wanted to get some information which were like variables. I don't know if this was your question.
Yeah, but you could, for example, just reduce the spatial dimensionality to the point where you have 1 point, 1 pixel. So you still have a little
Okay.
like P equals
Okay,
1.
yeah.
If you have like for
Okay.
pixel, you have P equals 4.
Okay, you mean to a fully convolutional network, but until when you get only a convolution with one pixel
Yes.
in order to get the... Yeah, actually, we didn't try that. We didn't try that, so this is something that maybe can be tried. Yeah.
Actually, I've tried. It kind of works. So just
Okay,
it's just
okay, you already
it's
tried.
not, I didn't, for example, try to actually put the feed forward once because what actually complicating the problem, and then I
Yeah.
removed it, and after I removed it, it was much simpler to train and everything. So I kind of asked myself, what is the actual goal of those layers there that I still don't know. So I was thinking that maybe you would know what is the why people actually do it like this, like because I've think
Okay,
I've seen other works with autoencoder, they always use that, and I've never seen an explanation why to use that.
yeah. Actually, we didn't try to not use fully connected networks in bottleneck. Actually, it's I neither thought about doing like this. I mean, a fully convolutional layer, fully convolutional neural network in which you at the end have one pixel layer. So maybe I could try to think so that now I can go with to an idea that maybe setting the kernel size and stride size maybe can be a little bit tricky when dealing with such small matrices when you reach the bottleneck. I don't know, actually, we didn't try. But if you tried, I mean, did you find any, I don't know if you found any advantages in doing that?
Did you find any advantage?
Yeah, in terms of training, it's just that when you put
More stable, something like that?
yeah, it's much more stable to train. It's much easier to train, and in terms of results, it's actually better because as in the other way, the other way, you could not achieve really low loss functions. It means, of course, it's going to be better because it has a better parameter. But
Okay.
it's just something that we are like trying to investigate.
Okay.
What is
Actually, I think that in general, using convolutions allows more sparsity during the training because you don't have all the connections, which is something that can be reached with a fully connected neural network, but adding some dropouts. But I actually have never tried using a fully convolutional neural network in this case for an autoencoder. Maybe I could try, but thanks for the suggestion.
Okay, more questions? You have? I have some questions. First of all, with respect to the dimension of the latent space, did you train when you reached the conclusion that P equals to 3 was the better choice? So what you were trying with the steady state case? Because for me, it was with a surprise that you have 3 variables of the latent space if you can control your problem by 2 variables, the angle of attack and the thickness, because this tells everything about your flow except if you have different regimes which, depending on the value of the angle of attack and the thickness, you will reach different regimes. And in that case, you could also split the problem in these different regimes, in which in each of them you will have only 2 variables of the latent space. This is one question, but I have another question, which is the fact that what do you think about your in this technique in which we're doing multiple steps? If you, instead of using, for example, this multi-fidelity, you could use also, you could put only one, you could feed your first autoencoder with only the angle of attack, for example, and then you will have, putting P equal to 1,
And then in the second stage, you would freeze P equal to 1 to try to learn what you get from the thickness in a similar fashion that you did with the viscous thing in the other case. So you learn the viscous effects because, and in the other way you didn't have, so you can learn the thickness effect, or you can learn the angle of attack effect by doing this multiple stage. What do you think?
Thank you for thank you for the question. There are two very interesting questions because so regarding the first one, why did we reach convergence with the 3 random variables instead of 2? So actually at the beginning we were thinking that okay, so our database is constructed with only 2 design parameters, so we should need only 2 latent variables, because 2 latent variables are because only 2 parameters are representative of the differences within the flow. So when we train our autoencoder with the static stall phenomenon, we were converging with only 2 latent variables, in fact. And then we expected to get the same results with the unsteady regime in which we have the airfoil dynamic stall, but this was not the case. In this case, we were converging with the 3 latent variables. We tried to understand why there was this difference, and we ended up with the consideration that when training an autoencoder, the number of latent variables should be at least equal to the database parameters, and investigating the latent space we obtained with only 2 latent variables, we obtained the answer. The answer was, in our specific case, was given by the hysteresis cycle we have in our phenomenon. What I mean is that if you can see here the lift curves of our dynamic stall database, we have this hysteresis cycle. And when we trained the autoencoder with only 2 latent variables, we had an hysteresis cycle for each airfoil in the latent space, which were crossing one to each other. So something like this, we obtained something like this. This means that for each couple of latent variable, let's say V1, V2, in this point, let's say, we do not have the unicity of the solution. And this was the reason why we were not converging, because of this, the loss of the unicity of the solution, which was found again if we added an additional latent dimension, so the 3rd latent variable. So explaining this phenomenon, should imply that we should understand actually what's the mechanism behind the training of an autoencoder, which is still an open problem. But we ended up with this consideration of finding this result, which was that the number of latent variables should be at least equal to the number of database parameters. So I don't know if I answered to your first question.
Yeah.
Okay.
First question.
Okay. Yeah, and regarding the second question, this is very interesting because we didn't try it, but it's something that we were discussing about. So learning, separate the effect of the parameters in our database. It's something that can be done. It's something that can be done, but we have many things to do, so we had no time to do that, but we were discussing exactly about what you were talking about. So first training with one of the parameters, then fixing it and training with the other varying the other parameter. And actually this method of sequential training with these I-star algorithms opens not only to what I showed you here, so extracting hierarchical latent subspaces or learning different fidelity from data, but enables also this, what you said, so learning the different parameters sequentially, or even you can imagine, for example, 2 different problems in which you move from 1D to 2D. You can predict such kind of things. So yeah, this is something that definitely should be tried, should be done, but we didn't.
Okay, thank you. I think my other question doesn't fit that well because of your first answer. But let us suppose you have, for example, that P equal to 2 would recover everything. Then this is a philosophical question. What do you think about instead of doing the so two questions related to that. One is, what do you think about training only the decoder part, entering, for example, the angle of attack and the thickness, and recovering the image? What is your point of view, the philosophical point of view of this approach, in contrast to the approach where you train the encoder as well? So let us suppose if you can have a function that maps the variables of the latent space into variables of the physical space. In principle, you could use only the decoder to train, and then after that you have this new set of parameters, and you enter there and you can recover your image. So from the philosophical point of view, what do you think about this other approach?
Yeah, so it's like training not an autoencoder, but a convolutional neural network, which predicts the flow field starting from the design parameters. Exactly. This is what you mean, right? Okay. Yeah.
Train only the decoder part.
Well, so it depends on your objectives. In sense that this is what I think. In sense that if your objective is just to make predictions, you can try to train just a convolutional neural network to make predictions. Using an autoencoder can be employed to extract some information from data. So for instance, here in this case, in which we extract some information which are also connected with the physics of the phenomenon. Imagine trying to use it on a physical system in which the underlying physics is not completely understood, or imagine to construct you want to construct a reduced order model for a system. And in this case, you would need the encoder part of the network. But if your objective is only to make predictions, so you can try to do the training only of the decoder. Actually, we tried it, but not on these complex problems. We tried on a very simple problems in which we wanted to construct. We only considered the geometry, so we only wanted to construct the standard distance functions around airfoils, and actually it worked. So, but you won't get some physical information from that. You won't get anything. It's just, I mean, let's say a pure transformation function from two numbers, let's say, so two parameters, and the output flow field. So I think that it can be done, but it depends on the objective you want to reach.
Okay, I have another question.
Yeah.
In fact, is a question is if you have tried something that we have tried, but we didn't get so good results. But I would like to hear what you think about, which is the following. You can once you have trained your encoder and your decoder, people generally attach the decoder part to the predictions, because they are saying, okay, if I give another set of, for example, the angle of attack and the thickness, I can predict what is happening with the velocity, for example. But on the other hand, you could use the encoder as a prediction, doing the following thing.
you could take an image that you haven't seen, and then you can find the latent space only with the encoder part, and then you can connect this latent space with an angle of attack and thickness, and then you can say, okay, from this new image, I can give you what was the angle of attack and the thickness if I use the encoder part. So this is another sort of prediction as well, but instead of giving the parameters and you find the image, you can do the other way around. So I would like to hear from you if you have tried this, and if you haven't tried, I would like to suggest you to try so that we can change knowledge on that. So to see if you, what is the error associated to, for example, the angle of attack and thickness that you get from an image that was not seen in the training part.
Okay, so now the question is only on the encoder part, right?
Yeah, is to use the encoder part as a prediction tool for the
for a
parameters
thickness. So once again, in this case, we tried something with only the geometries, and what we found is that, for example, if we train the encoder to provide an input to the sign and distance function of airfoil changing, in this case, the thickness and the camber, on a database composed by NACA 4-digit airfoil, for instance, then it was able to predict the airfoil thickness and camber only of NACA 4-digit airfoils, because when we try to provide an input, a new image of a new airfoil in which was not of the NACA family, but in which you are changing, you have a certain thickness and camber, the prediction was not the correct thickness and camber. So it was like providing an input, an image which was far away from the training data. That in the sense that if we would like to make a parallelism with the physical phenomenon, it's like providing a new physical phenomenon. So it's like it's like the encoder itself, trained to predict the thickness and camber, was not actually capturing the thickness and the camber of the airfoil, but was capturing the thickness and the camber of an airfoil belonging to the family of airfoil in our training database. So it's something that should be, I think, deeper investigated to better understand the dynamics behind the training of such kind of algorithms in general, of such kind of neural networks. I don't know if this was your point.
Yes,
the point of your question.
It seems that is somehow more difficult to use the encoder as a predictor than to use the decoder. So I was just wondering if you have tried something that. Okay, but thank you for answering.
Yeah, thanks for your question. Very, very interesting.
Yeah. So okay, so no more questions. Thank you very much, Arthur.
Thanks to you, and thanks for inviting me for doing this talk.
It was a really nice presentation. So thanks. Next time.
Thank you.
So I'll keep in touch about the certification and so on. Okay.
Okay. Thank you so much.
Okay. Thank
you.
you.
And have a nice day. Bye.